Hello and welcome to video 5 in lesson 2, where we will be talking about advanced linking. In this video, we're going to introduce a few advanced linking concepts, and we're going to talk quite a lot about the benefits of numerous links and advanced linking in your functions. And we're going to look at an example from road vehicle analysis. So this video will be quite short and sweet, but I don't think we're going to complain about that. So the reason for advanced linking is that a system of energy and economics is very complex, meaning that we have a lot of interdependence within our system. So quite normally we will try to make something maybe that are a bit in silos, but interdependence, generally speaking, is quite difficult to obtain in a non-optimization model. So we can actually do that in Leap, and complex advanced linking is a way to do that. So we will be talking about quite a lot of linking and also a little bit about some functions concept that could be useful. So here I have an example of advanced linking in Leap in a transport model. So what that does is that if you look at it here, so this is just one of many. This is for the fuel economy of the ICE petrol car. I think here we have. So you can see it's actually a little bit. It is so big, in fact, that it runs out of space. So we can't actually see what's going on. So that's why we have the builder tab here. And what we can see, what we really have here is numerous different things that are just multiplied together. We have taken a bit of a look in lesson 1 around this, but we can have an easier view by looking at the. So this is the same thing, but elaboration. So you can see we actually have 6 different specific parameters from key parameters or key assumptions, all under the transportation umbrella. So here, for instance, we have our standard car fuel efficiency. We have a sizing factor. We have a engine type factor, and then we have, in this case, 3 improvement technologies, which are factors that relate to the projection on gasoline engines particularly. So, and these are multiplied together for this particular type of vehicles. So what we can see here now, I try to pull out all these key assumption transportation. So you can see that's the one folder we are just in, and below that we have quite a lot of key assumptions. Among that, standard fuel efficiency, which we use for this particular one, and then we have the size factors, which has a number of different types, and this is for all different vehicle types within the category. And then the same thing is happening here, that we have the vehicles type factor, and then we have all the different vehicle types we have represented in any shape or form in our model. And then other than that, we have the ICE improvement technologies, which is, it's actually kind of misnamed because some of them are being used all the places, like air assistant design and light materials, and for that matter, regenerative braking. Not so much in the electric vehicles. We don't actually use that because it's already there. But that means we have quite a lot of places we have to get have a control over. So if we were to switch from a instead of the ICE petrol car, it would be a MPV diesel, a diesel MPV. Then suddenly we would have to look at the sizing factor for the MPVs, and then also the road vehicles type factor for diesel, and then we would have a number of these different things we can use in diesel vehicles, but that are different than from the petrol vehicles. Now, why would we want to do that? Well, the benefits of that is that we can make a few generalized formulas based on a few key references, key assumption references. Now, these can of course be a little bit different. So we had a folder we were always referenced to, but the actual key assumption was we had to differ that in our different types. And then for our different engine type or motor type, we would also have to change that. But that means we can refer quite a lot of things. So in all our MPVs, we can refer back to MPVs, which again refer some parts back to the standard petrol car. And in all of our different vehicle types, we can have the factor assumption between diesel and petrol. So for an MPV diesel or for a truck diesel, we have the same factor compared to gasoline. So in that, we can actually simplify the way that we do it and actually how we think about things, even though the formulas themselves become quite large. With some of these, we can directly use some things like the standard vehicle efficiency. If we have to do a calibration on that, then that would change every other road vehicle in our analysis in this case. And that means we have a few key assumptions that can change to very large parts of our results if we were to change that a little bit. And sometimes we want that if there are really general. Some of them, if they're really macro, we can like GDP, we have a tendency to refer to that a lot. And writing them down one by one in a place would be quite bad. And we can also refer that back to growth as with an elasticity that's really meant for something like this. But we can also do that with some very micro things. For instance, we have some specific factors for some technologies that are used in some kind of other technologies as well that could be related, and that can really be used numerous places, which is quite nice. The other thing we can also look at is not only can we have inheritance between scenarios, we can also shape our scenarios in such a way that not only do they depend on a different reference or reference key assumption, but it can also change with it. So in this case, we have two scenarios. We have mitigation and reference, and we have basically put in the same income growth rate, or the same growth, and as you can see, it depends on income growth rate. But these two are slightly different, so they will change over time. And that I'm just showing you what we have here when we are reaching around $10,000 per capita. What we instead can do, which could be very interesting, formula. So up here we have made an if statement or an if formula. So this is a conditional formula we have made. So, and it's the exact same formula in the two scenarios, which is why they follow along with each other perfectly. But because we have made some changes into our mitigation scenario here, as for testing, we can actually see how these two split, because if this gets told, if you are coming more than if your income per capita is over 10,000, then you need to adjust your growth rate. So that is what we do here instead. So we can see this mitigation scenario, when it reaches that, it goes with a 2% growth rate, where the other one continues with a 6% growth rate, because the final the GNI per capita hasn't reached 10,000 yet in the reference scenario. So that's how we can actually make something like a elasticity is dependent on the actual GNI, so we can have dynamic models. So we don't actually have to change them if something macro changes, but we can have them change themselves, which has a larger impact, which is quite useful to have. It's usually not something you have in your first iteration of your model. It's something that usually comes later when you realize that there are just some dependencies you want to change quite a lot. If you make that into an if statement instead, which is quite easy in Leap, and there is a nice little wizard for that in the formulas builder, then you can make them dynamic to change to certain areas in your scenarios, which is very, very useful. So here I'm just going to show you a few different methods. This is the one you saw before, and this basically means here we have the if the key income in $1,000 is above 10, so if the income per capita, which is above 10,000, reaches above $10,000 in any given year, then your growth rate from the beginning should be 1, but after 2020 it should be 2, which means in this case, as soon as we hit the $10,000 threshold, it switches to a growth rate of 2. And if that doesn't happen, well, it's still going to be 1%. In 2020, if you haven't hit the target there, it's going to be 3%, which it is. That's what happens in both the scenarios. But if you haven't hit it by 2030, it should go to 6% instead, which just happened just for one of the scenarios. So that is quite actually kind of amazing that you can make dynamic dependencies between two variables. Now, we also could do some of these that are quite cool as well. We have base scenario, base year, and also here we have an if on a previous year's value. So if the year before, the one I'm calculating, were over 10,000 in this case, then we should go for an interpolation that says in 2040 we should have 20,000. If not, then the 2040 should just be 15,000. And that basically means if we have a big enough growth rate, maybe depending on other factors as well, then we're going to have a higher growth rate going forward. And if not, well, then it's not going to do that. This one I don't think I would recommend, because I think if you reach this in, let's say, if you reach 10,000 in 2035, then you will have a bit of a chart going as up here, and then at some point you might hit the threshold of 10,000, and then you might shoot up to 20,000, and if you don't hit this the threshold, you will just go, or you will actually go to this to a 15,000 instead. So that could be a bit complicated, but if you presume you're probably gonna hit this number, you can use this previous year value, which is the important part of this if statement. You can use it for quite a lot.